Hello, folks. Welcome, everybody, to this new lesson of robot programming. All right. So what we will be doing today, to my one single concurrent viewer, is to continue the lesson of last time. So last time we have seen. Please write if the audio quality is sufficient. It seems yes, but I'd like to know from you. Last time we introduced ICP. ICP as a technique, a family of algorithms that are used to register typically two-point clouds. Registering two-point clouds means finding the transformation. With transformation means a rotation matrix and a translation vector that maximizes the number of overlapping points after the transformation. I will just quickly recap the slides of the concept of ICP. Of course, on a different window. Why two? Both. All right, here we go. So the game of registration is the following. We have a set of points in the word frame. They can be either 3D or 2D. You can imagine that these points have been acquired with a sensor such as laser rangefinder, laser scanner, or a depth camera. But what we have is this set of 3D points that represent typically an object, a portion of the scene in the environment. And this is our initial input. Then we move a bit with our device and we get from this sensor another set of 3D points acquired from its own new location, right? The two point clouds, the two set of points will resemble each other because they are acquired hopefully at nearby locations, but they will not be really the same because the sensor moved when observing the one point set of points from the new position. Okay. Now I tell you that if some oracle would provide us with the correspondences, which means given the two set of points, if someone would tell us which point in the first set belong to the point in the second set, in a sense that they refer to the same instance of object in the word, then calculating so this is the reference frame of the robot, of the new sensor. This is the initial reference frame from where we acquired the points. If I would know that this point corresponds to this point corresponds to this, and so on, then I could easily determine the relative transformation between the two reference frames just by calculating the transform that minimizes the distance between each point and in the first cloud and each point in the second cloud after applying the transformation. Which means you apply the transform, you obtain such a situation where the points typically overlap, and then you can define an error, which is the distance between the point and its counterpart, And then once you have done that, then you have implicitly determined the transformation, which is the one that maps this reference frame into this reference frame. Is that clear? I hope so. So this is the concept, okay? Now, we are in robot programming, but we have to deal with real case examples in order to test our skills. Well, this was an example, but now let's see if I find an ICP video example. Yes. Okay, maybe I can provide you an example of how ICP works. You start from a configuration like that, where you have the red and the blue point clouds, and then at each time you determine the correspondences according to some sort of initial guess. You execute the optimal. Yeah, it's nice. Huh? I don't know what this thing. I'm on an anonymous browser, but it decides to show me advertisements. So the idea is that you have these 2 point clouds and you morph them onto each other. Okay. Now the game is that now this GIF for whatever reason doesn't work, and we will live with that. I know why it doesn't work. No, I don't know why it doesn't work. Whoop. It used to work. In this case, you should see the two surfaces coming together, basically. Now, with the tools that we have, how are we going to implement this mechanism? Well, let me tell you that assuming that you know the correspondences, so these vectors over here, the transformation would be extremely easy to get, doing some little mathematics that is explained in probabilistic robotics and also a little bit in computer vision. Okay, and this part of the program is already given to me by me to you, which means that we will have to focus on the other part, which is the part of determining which point in the one cloud is which point in the other cloud. ICP typically is an iterative process that alternates two phases. You start from initial guess, where you have the two clouds, let's say, off from each other. And then given this initial guess, you ask the system, you ask an oracle, can you tell me, given this configuration, which point I take the first point in the cloud, let's say this one, which point here corresponds to which point in the other cloud corresponds to this first point here. And then you do some sort of search. Typically it's a nearest neighbor search, and then you say, okay, this point corresponds putatively to this point over here, right? Then you take a second point, let's say this one, and you say, to which point is this point corresponding? Typically, you have some sort of heuristic. The simpler one is that you consider the transformed point in the cloud, and you pick up the point in the cloud that stays fixed that is closer. Okay? Now, to make you an example, and this basically for each point of the input cloud, of the moving cloud, will give you an idea of which one is the closest point in the fixed cloud. Just to make you an example, think about a configuration like that. Now, if the situation would be the following, we could trivially, it's not, we could trivially assign the correspondences. Okay, what is the closest point in this cloud over here to this point over here? You might say that it's presumably this one over here. So there would be a one correspondence going from here to here. Then you might ask, what is the closest point to this cloud to this? Then you say, okay, to this second point. Then you might say, okay, it's this, right? And so on. normally, if the clouds are far apart, this doesn't really work. But if the clouds are close together, like, let me say, if I do something like that, if the clouds would be close together, like in this situation, now it would be easy to say, okay, this point matches with this point matches with this point, I don't know, probably with this. And this is typically the situation that you find in iterative matching. So basically, by a simplistic nearest neighbor search, you determine which point belongs to which other point. This nearest neighbor search is clearly driven by the initial association, which means if you are too far off, the initial guess of the estimate, which means the relative transformation. If you are too far off from the estimate, this process is not going to converge unless you use something particular and different to calculate the nearest neighbor. Is that clear? So now we can imagine a situation like that. Let me try. But we have a situation like that. Move it here, right? Now, if we start from a situation like that, how the algorithm will evolve would be this point is assigned to this point is assigned to this point presumably is assigned to this point is assigned to this, and this point is assigned to nothing because maybe it's too far, right? Conducting an optimization, so this to this, this to this, this to this, and this to this, and conducting such an optimization, like by nose, would bring me to shrink this distance, this, and also somehow this. So I presumably will reach a configuration which is the following. Try again. No. Right? And this will be the second iteration. At the third iteration, I have the correct association. At the third iteration, I will, oops. No. At the third iteration, I will associate this with this, this with this, this with this, this with this, and this with this. I will conduct an optimization that will finally bring me to the position that I want, where I want to be. So this is more or less the behavior of ICP in operation, right? So we can now abstract to the generic algorithm. So basically, when we design an algorithm, we have always to consider what is the input of my program and what is the output that my program wants to generate. Well, the input and also the output is the initial position of the two clouds. You have seen in the process that there was one cloud that I was moving and the other one that was staying fixed. When I refer to cloud, is it now clear that I'm referring to a point cloud, which is an unordered set of points? So the X is the initial position. Then we have a set of points in a moving set and a set of points in the fixed set. ICP works by running iteratively and refining the estimate of X over multiple steps. Each of these multiple steps is composed of two parts. The first part is to determine the pairs between a moving point and a fixed point based on some similarity criterion. Right now, as similarity criterion in these mechanics, we will choose simply the nearest neighbor under the transformation, which means we take mi, we apply the transform x, and this way we will be moving after in the position where it should be according to x, and then at this point we look from this location the point in the fixed cloud that is closer to the transformed point mi. So this is what we do for determining the correspondences. And then there is the optimization part that, as I said, it's given by me and it's for free, so you don't need to care, right? This was the game. And so our naive implementation will work as follows. We will have to compose all the structures. Typically, ICP requires to do a lot of searches at each iteration. How many searches? Well, as many as the points which are in the moving cloud, right? So potentially many. Over an other cloud, which is potentially equally big or even more, which is the fixed cloud. Our idea would be then in the implementation to use a KD3, but in terms of correspondence heuristic, I have already written here what we need to do. We need to, given the current transform X, we need to calculate the position n prime j of each point in a moving cloud mj, and then we have to find as corresponding point in the fixed to mj the point that falls closer to the transform point m prime j. So let's say fj is the point in the fixed and prime j is the point in the moving. After the transformation, we have to find the closest. Okay. Once we have done that, our correspondence heuristic will return a pair which is consisting of fj and m prime j, the already transformed point. Why the already transformed point? Because I want so, because this simplifies me a little bit the mathematics in the optimization. Okay, you could also return nj, so the original point, but then in the optimization I will have to recalculate the transformation, which costs time, and I don't need it, given that I have already done it in the search, in order to calculate n prime j for computing the heuristic, right? So now we will go to your tasks that you will do today, but before, let me explain you the algorithm that I have that we were constructing before. Okay, so let's go to the editor. The very first thing, so now we are in the domain of designing a class that implements this algorithm. So the very first part of designing a class or a struct is in general to decide which data entities we have in the game. Now, from the for simplicity, given that it's a little bit more algorithmic rather than syntactic, this task, I will restrict myself to a version of ICP that operates on 3D points. Okay, your task will be later, maybe after this lesson, the one of crop it down to the 2D case. So we define vector 3f as a vector of 3 components on a pair of floats. This is a type def of eigen that stays for eigen matrix float 3, 1. This is the meaning of this vector 3f. We define, the second thing that we need to do is to define a pair, a pair of points, because in ICP, if you remember well, our goal was to calculate a pair consisting of a point in the fixed cloud and a point in a moving cloud, okay, potentially transformed. So let me define this other object that I call point pair, just for simplicity, that stores inside itself a vector 3f that represents the point in a moving cloud and a vector 3f in the fixed cloud and a vector 3f that represents a point in a moving cloud. And I also I'd like to have it easy and to assign these points on construction. So I define a constructor, and in the initializer list, I assign this parameter to this field with this line, and I assign this parameter to this field with this line, right? Also, I make you notice that this is a struct that contains eigen objects, and so we need to put this macro here at the beginning, and this is what we were doing last lesson. An additional thing that we might need to do is to have a data structure that contains these correspondences. Now, I here define class object, a type that I'd say it's a vector of this point pair. So it will be a vector of correspondences, where each element contains a point in the fixed and a point in the moving, right? Let's call it point pair vector. And it's clearly a std vector, so using the standard library vector. But then we have, given that it contains eigenobject, we have also to specify that these points will be aligned to 16 bits, to 16 bytes. So we have to add this additional parameter to the template. Otherwise, it defaults to the standard allocator of the STM. Okay. So doing so, we have defined our pair point. We have defined a class or a struct that is able to contain pairs of points, and we have defined also a vector of these elements over here. Then we can go on and define our ECP class. Remember and consider that the dominant operation in a search of correspondences will be the one of looking, given a fixed cloud, looking for a point in this fixed cloud which is closer to a query, which seems pretty much the task of our KD3. Okay? Now, for simplicity, we assume that we want to have our ICP, but this is just a choice, operating on a standard vector of points 3f, which means that the clouds will be offered to our ICP as a standard vector of vector 3f. We could also go for a fully template implementation that infers automatically the type, but let me go slow and then we can generalize on it. So we define for our convenience a type inside, we call it container type, which will be a vector of point 3f. Once again, the vector is a vector of eigenobjects, so we need to declare the aligned allocator. Additionally, another thing that we will be doing, and please go back to the KD3 in case you have still doubts, is to use inside this ICP a KD3 to conduct the searches. That clear? So we define a class, we call it 3node, which will be a 3node of our beloved KD3 that we have seen before. Okay, all right. Then before going on with the rest, I'd like, with the constructor and whatever, I'd like to populate my class with the data members, which are the data that I do require in order to do the calculations. Let's start putting the types that I need for sure. Now, the first type that I will for sure need is an isometry 3f. Look at the eigentransform. An isometry is nothing else than a rotation matrix and a translation vector in 3D. Okay? Is a way, isometry is a transform that like if you apply an isometry to a point, P, you have R, P plus P. Okay? We have seen it already. If you apply an isometry to another isometry, R1, X1, X1 times X2, let's see, these are two isometry, then this is equivalent to R1 times R2, plus, and then in the vector you will have T1 plus R1 times T2, right? This is stuff that you might have seen in robotics 1. And of course the same holds for 2D, only that the rotation matrix becomes 2 by 2 and the translation vector becomes two-dimensional. All right? Okay. We say our isometry type. I mean, willing to be like elegant, because then maybe you want to do this will ease the exercise later on. Later on, we can say using eigen isometry at 3f and then here we can write transfer type. Right? All right. This is the very first variable that I need, because this transformation will be refined during the iterations. Then we remember what we do during our game. We have a container. We have two container of points, and we would like to basically at each iteration take an element of the moving, apply a transformation x, and find the closest point in the fixed. And then once we do, and compose a correspondence. Then once we do that, we call a magic function which is called optimize correspondences that will do side effect on the x variable to return us an improved version of the transform that minimizes the distance between corresponding points. Okay, this is our game. All right. Now we can easily say that the moving cloud, so the cloud that is going to be moved, technically never changes, because every time we do a search for a point in the query, for a point, we just like take this point, we transform it, and we do the search, right? We don't alter the data inside. So we could save memory and define a data member, which is a const reference to a container, which is a const, basically it's a pointer to the moving, and we ensure that our moving cloud will not be changed. Conversely, the fixed cloud, which we pass over here, will be altered because, if you remember, because we have decided to conduct the nearest neighbor search on the fixed using a KD tree, and the process of constructing a KD tree alters the position of the points inside the cloud. Okay? Clear? And then, to this extent, it makes a lot sense to make a deep copy of fixed. And we do this, and so we will declare a new variable. So this is a copy of the fixed cloud that we pass here. Remember that to initialize the KD tree, we will have to say the range, and we will also have to say the number of points in the leaf. These all operations will be done in the constructor. So the next step will be to create a constructor that populates our, initializes our KD tree. Let's say that x, the transform is always the identity, otherwise I could pass it to the constructor. I could pass it also as a default parameter. And this way, basically, each time I construct ICP, and then here, x, right? All right. Mean points in leaf. Yes, perfect. But I don't like. Okay, we could do this. In this way, we exposed another parameter. If we don't set the transform, it takes it as if it was the identity. In the constructor, we assign the transform, we assign the fixed cloud, we assign the moving cloud, and then remember that the tree is a special class that requires a constructor, because if we look at our KD tree, if we look at our KD tree, it defines a constructor, which means that we have to call the constructor of the KD tree member in the constructor of our class. And we will be doing this at this line, right? After having copied the fixed parameter in our fixed member variable, which is this one over here. Okay? Very good. Another utility that we could do, but this is not required, but I feel like it's a gentle action, is to think about how this algorithm will operate. It will operate, and each time it will construct once the KD tree, and then for each iteration it will take the moving cloud, it will apply the transform, it will construct a vector of correspondences, adding all the elements to the correspondence vector, and then it will invoke an optimization that will alter the x variable, right? So just to understand how there's a method that I call here run, and I will show you the method run. Don't look at it. The method run, so this is, ignore this, but for each iteration you compute the correspondences and you optimize the correspondences. The rest is just like for me to print some stuff. This will be how our algorithm will work, okay? Now, clearly we will have to focus on compute correspondences and optimize correspondences, right? Another variable that I need in my system that I didn't mention is clearly a vector of correspondences. Obviously, I could decide to calculate this vector as a temporary in my function, given that the loop of ICP is finding me the correspondences field, and then I could say, okay, optimizer, take these correspondences. I mean, I don't like spectacularly this idea, because each time you create a new vector, you're gonna stimulate the heap. So in contrast, I'd like to have a member variable that I remember, that I modify doing side effect in my class. At the end, the only method that I will expose in this class will be simply a method to access the constructor, a method to access the transform, and a method to run, and nothing else. The rest will be protected inside the class. So the reason why I decide to have a member variable instead of declaring a temporary somewhere is to avoid useless memory allocations, okay? And here I have my vector of point pairs. So these are all the variables that I need in my class. Agreed? Very good. Then there are two functions. One function that is called compute correspondences. This is for me to test, and I will blast it. And the other function that is called optimize correspondences. And then for beauty, I think I added a couple of other variables, other functions. So these are the accessors. These are all accessors to member variables. We have a method which we call x round bracket close bracket that returns the state. Another method that returns the state. We could also write it in line. We could also write it. These are not necessary. It's just sugar. We might have a vector that returns the number of correspondences. Remember that while conducting a search, we have to search up to a maximum radius, right? And so it's not said that each point in the fixed cloud will correspond to something in the moving cloud will correspond to something in the fixed cloud, because we have a certain maximum radius of search that we want to be under. And then this is for the optimization. Ignore. Okay, then I can start blasting what I've done before. Public, we will only have a method run, and then these methods will become all private. Okay? This is for the optimization, ignore for now. So all clear with the constructor? Yes. So like now, given that it's disturbing me here, ECP Okay, I will just move the constructor in the CPP file, right? This is the CPP file. I had already written it, but just to be consistent. And then clearly here I can erase it. Okay? then it will complain that it doesn't want default parameters in the CPP. All right, so I have defined the public interface of my class that allows me basically to read data. Why do we have two versions of this method isometry3f? Because, well, by using this method, we could also assign some initial guesses as we want in the middle of the iterations, just because we want. But if it confuses you, we can just blast it. All right. Now, these were the variables that we have put in. Yes, we have a variable that we called kd3. We have a container which will be we called fixed. We have a variable that we called x. We have a kd3, and then we have additional. I think this was point pair vector, the correspondence. Okay. Yeah. Transform type. Let me be consistent and well, let me call it transform type. Okay, is that clear? Now we have to focus on basically just one method that we call compute correspondences, and I will now push this revision, and I'd like you to try to implement it with what you already have. Now let's go briefly to the CPP file, and then I will push clearly, no? Solutions. No, don't show, don't show. No, you stop it. All right. This is for me to test, but I know it works, so I will ignore it. Okay. Run. Okay, now all we have to do, void no. that clear? What I'm asking you to do now will be pushing. I don't know if you have it in your public repository. Let me check. No, you don't have it. No. Okay, folks, the exercise is provided. I'm willing to respond questions. Yes, probably there is some bug because I never tested it. And Antonio tells me there is no comma. Antonio is right. And probably it doesn't even compile. I have to do it myself now to be sure it compiles because I was writing it in open loop. All right. So is that clear? So remember to put a comma here, otherwise the compiler will cry. Right? Is the task clear? It's all here. You just like go in the folder exercise in class into RP08 ICP and you start doing it. I'm staying available for questions and whatever, what else you need. Okay, try to do it on the spot. It should take no time because you have already done it. Let's say 15 minutes, or yeah, 15 minutes should do. I will now mute the streaming and everything because in this way we save bandwidth, which I think no, it's like, why do we need to waste bandwidth if we don't need to? Okay, so I will just switch off the audio, the video, and in a way that we will save bandwidth and everything, and but the chat is active. Folks, seems to me that the majority has agreed to go for lunch, and well, then it's useless that I let you waiting, and then you do the exercise, because then we will build on this exercise. Let's meet at 1:20 or half an hour for lunch should be okay. Okay, 1:20, and then we're back. Do the exercise. I will ask how many.